Welcome you all. In this video, how we can generate and visualize complex exponential signal in MATLAB. So as you see here, complex exponential signal can be mathematically represented in both continuous time and discrete time as follows. In a continuous time, the complex exponential signal can be written as e power a times of t into cos omega t plus j sin omega t, whereas in a discrete time, signal can be represented as e power an into cos omega n plus j sin omega n. Right, now let's see how we can build and visualize this signal in a MATLAB. So first we should create a new script, and then let's save this file. Complex exponential, right? So as we know, first we should create a x-axis data. For a continuous time, we have to have a time vector. For a discrete time, we need a set of samples, that is a sample vector. Okay, so let's create. So we know already how we can build the x-axis data, so I just take that from the previous program, copy and paste it here. So I just remodify this as complex exponential signal, right? Okay, so we have a time vector which is starting from -10 to and ends on +10. Then we have a samples between -10 to +10. Now for each of the time frame, now we should create a amplitude, okay, by using an appropriate function. As we know, for a complex exponential function, we should use the function called e power at into cos omega t plus j sin omega t in the case of a continuous time. Okay, let's put this equation over here. So I'm going to consider the amplitude as y1, which is equal to e power at. So e power in MATLAB can be written as exp bracket. You should open the bracket, then you have to keep the a and t. So as we know, when we keep a as positive, then it is going to be exponentially increasing, and when we keep a as negative, then it is going to be exponentially decreasing. Let's assume now a is positive. Let's fix a as 0.5 into t, okay, into, we should multiply this with the cos omega t plus j sin omega t. But what we have to do is, this has to be multiplied, this actually a row vector, because this operation is going to be performed for each of the time, which is like for -10, then then -9.999. so for each of the time step this will be done. So we have to multiply this with the cos omega t plus j sin omega t for each time step. So as we know, whenever we used to perform a multiplication for a vector, for each data in a vector, we will go with the dot into. So this dot will helps to perform a bitwise multiplication, which means the first variable on this vector will be multiplied with the first variable on the cos omega t plus j sin omega t. Okay, right? That's why I'm using this dot symbol. Right, now let's create a cos. So cos, open bracket, omega t, right? So omega means we know it is a 2 pi times of f. So let's put 2 pi f. Okay, let's fix frequency as 1 into t, okay, plus j sin omega t. Actually this entire term should be multiplied with the exponential, so better I'll open bracket here. Now j into sine 2 pi frequency, let's take 1 into t. Okay, and now you close the bracket, right? So now this entire term is going to be multiplied with e power 0.5 times of t. So this is going to create an amplitude for each of the time, right? So now we made amplitude. Now we go for making a plot. First our x-axis data t, and then y-axis is y1, right? Now we go for labeling the x-axis, y-axis, and also making a title for the plot. So we take that from our previous program and paste it here. Let's keep x label as time, y label as amplitude, and title as complex exponential signal in a continuous time. Okay, right? So this is going to make complex exponential signal in a continuous sense. It is actually going to make a exponentially increasing signal, because I consider here a as a plus 0.5, right? Okay, now we create for a discrete time. So first I just provide a space for the plot using a subplot command. So subplot 2, 1, 2. Okay, right? Now I will create an amplitude in a discrete time, so which is going to be taken as y2. So y2 equal to I copy this and paste it, and I just make a modification, because in a discrete time this function can be expressed as e power an into cos omega n plus j sin omega n. So only thing we have to replace t with now n. So let's copy and paste it here. I just modify this t as n, and this t as n, and also this t as n. Okay, so save this. Right, now we made a amplitude. So we go for making a plot, and as we know that to make a discrete plot we will be using a command called stem. So stem x-axis y, and y-axis is about y2, right? Okay, now we go for labeling the axis and also making a title for the plot. So I just copy paste here, and I modify. For a discrete time the x label is about sample, and y label is about amplitude, and title we can keep complex exponential signal in a discrete time, right? So now you save this and you run this program by using a run button. Now you can see here our exponential signal, that is a complex exponential signal, linearly increasing. And similarly you can see in a discrete time the signals are getting also linearly increased. But as you see here in a discrete time we won't see the symmetrical form. We are getting only positive data, there is no negative data at all. And whereas if you take a continuous time we have a symmetrical signal. The reason behind, actually the discrete time signal is about a discrete value. So signal is available only at no particular time instant, and all other cases the signal is 0. So if we wish to see the proper plot, what we can do is we can keep that omega data as in the order of pi by 2 or pi by 4 and so on, so which will have a clear visualization of a complex exponential signal in a discrete time. So what I can do is I just remodify this omega, which we kept it as 2 pi of, as let's keep as pi by 2. Okay, right? This I am doing just to see the signal in a proper form, right? So I am just taking omega as pi by 2, and similarly here I am taking omega as pi by 2 into n. Right, now you run this. Now you can see that the signal is getting linearly increased, in a discrete time also, right? Thank you.